Hello everyone, my name is Eric Larson. I'm an artist living in Vancouver, Canada, and this is my second submission to the Summer of Math Exposition contest. I submitted my first entry this morning, and in the process I realized that we are allowed to submit more than one video. So this afternoon I decided that I do have some more what I think is interesting content to share. And so again, it's going to be on a low-tech type of presentation, just me with some paper and my whiteboard and a pen. But what I'm going to be sharing with you in this video is the reason why our numerals look the way they do. So in my first video, I shared with you that somebody created the 360-degree diagram using base 12 geometry. So we're talking about base 12 geometry. And what I realized is that in the course of my explorations into base 12, that whoever it was that created 360 degrees also created the design for our numerals. So this may be a little bit of a controversial topic also, because right now I don't really think there is any official reason that they look the way that they do, or there's no logic behind why the numerals have their specific designs, or it's a little bit vague as to who may or may not have actually come up with their design. But what I'm going to do in this video is show you what my hypothesis is as to why the Western Arabic numerals have their specific designs. I believe that the person or the group of people or the culture in general that designed them was using base 12 math and base 12 geometry, and they used a very intelligent thought process to come up with the various symbols that we now call the Western Arabic numerals. So to start, I'm going to introduce you to this pattern again, because this is the pattern that they used to come up with the various designs. What they did was they went to the corresponding circle in this series and looked at its relationship to the grid beneath. So there's a whole lot of lines in there, as you can see, and they used the relationship between that circle and the grid to come up with the various circles and straight lines, or part circles, angles, all the different elements of the numerals to come up with the various designs that we now call the Western Arabic numerals. So first, just quickly go over how we come up with this pattern, and then I'll show you what I mean by going over each numeral step by step. So again, we draw a circle either on a line, or we just draw the circle, put our compass down, keeping the radius the same size, and draw another circle with that point on the circumference. We draw another circle. Each time we draw a circle, they're intersecting the original circle. We put our compass down on those new points. We keep drawing circles until we get to this point where we have intersecting circles that create points that are perpendicular to our x-axis. We have our y-axis. We continue putting our compass down on those new points, draw more circles until we get to this pattern. Then we start connecting those points to generate all these radiating degree lines. That's the pattern that we use to come up with the beginning sort of structure for the 360-degree diagram. But we can continue to connect those points in a different way by putting our compass in the center. Now we're going to adjust our compass to start meeting up with these other points in this pattern. And you can see here we've started to generate circles, and these circles have the radius. The second circle has the radius of the square root of 2. The third circle has the radius of the square root of 3. Fourth circle has the radius of the square root of 4, and so on. So what we're going to do is we're going to look at, again, the relationship between the circle and the grid beneath to come up for the design for the numeral. So I'm going to start with the numeral that represents the number 2. That's the first one that I discovered. I was drawing a lot of circles with the radius of the square root of 2 in my explorations, and one day this symbol kind of jumped out at me, and I was thinking, that looks a lot like a 2. So what I'm going to do is just change up my board here, and I'm going to show you what I mean, and I'm going to show you all the hidden geometry and information that's contained within each numeral that has to do with the number that it's representing. Okay, so here is a larger version of that same pattern. And what we're going to do is look at the second circle in the series, the circle with the radius of the square root of 2, and we're going to look at the points where that circle is touching down on the grid, or where the lattice points are that define its position. So again, here's the second circle, so we can sort of see it's basically, this is one of the lattice points, this is one of the lattice points, this one here, and that one there. So those are the 4 lattice points that define the position of the circle with the radius of the square root of 2. So now what we're going to do is simply connect the dots by tracing some of the lines, between these points. So we're going to start here, and we're going to just trace the circle, the arc of the circle from that point to that point there. Then we're going to trace this line going right through the middle, the 45-degree line. And then I'm going to trace this line along the bottom here between those 2 points there. So there we have a very geometric pattern that represents the number 2. It has all the qualities of the 2 in the sense that it has the curved top, then it goes from the top here down to the bottom, and then the flat bottom. And what's really interesting about this symbol is that this bottom line here is the length of 2 when we see it fitting on the grid like this. And this is a quality that all of the numerals have. They all contain a line or a distance within their design that contains the value of the number that they represent. So in my explorations, when I discovered that, it really helped me to focus in on the actual dimensions and proportions of each symbol. So I'm just going to write that down here, actually, that this number contains, or this symbol contains the length of 2 within it, and it also contains the length of this line here, which is 2 root 2. Again, what else that the symbols have is they contain a lot of sort of extra information than just the number. There's a lot of geometric information encoded within the symbol. And that's what I'm going to be going over, because we also know that the formula for the circumference of a circle is 2 pi r. So in this example, r, the radius of this circle is square root of 2. So this length, this portion of the circle is 2 pi times the square root of 2 divided by 4, because this section of circle is a quarter of the entire circle. So we can cross that, knock out that 2, change that 4 to a 2, and so the length of this portion of circle is square root of 2 pi divided by 2. So I'm going to put that down here. Square root of 2 pi divided by 2. And then I'm going to put the whiteboard behind so you can see that a bit more clearly. Okay, so all this information is encoded within that symbol, and that is the original version of the numeral that represents the number 2. And all the 2's that we see around us, all the various fonts and whatnot, are all based on this symbol. Perhaps it's more curvy and there's a spiral there or something, or a curve and a loop and all that. But basically that's the bones of the symbol, and that's what we're going to be looking at now, is the bones or the skeleton of each numeral, how it emerges or was originally designed from the relationship of its corresponding circle in the series to that grid beneath. So what I'm going to do now is jump a little bit to the numeral that represents the number 4, because that enables me to continue using this diagram. So I'm just going to clear this off, and we're going to look at why the numeral that represents the number 4 has the distinctive shape that it does. Okay, so here we are again. So what I'm going to do now is go to the 4th circle in the series. And again, I'm going to start by marking off some of the lattice points that define the position of that circle. We're going to go to the very top point where we have our y-axis here, that point there, and then all the way down here to the bottom. And I'm basically going to draw a line between those 2 points just like that. So there right away we have a line that is the length of 4. And now what I'm going to do is go to this point out here, again where the square root 4 radius circle is crossing this line here, and I'm going to join those 2 points together. So I'm going to do this freehand here, something like that, goes to that point, and then I'm going to draw a line along the bottom here, going to this point here, where this degree line is crossing, again, the I guess that's the -1 on the y axis. I guess that's how you say that. And there's the design for the numeral that represents the number 4. So just going over all the lengths again that are contained within the symbol, we have the length of 4 there. We have the length of 3 also included in that symbol. We have the length of 2. This entire line here is the length of 2. And then we have the length of 1 here at the bottom. Let's write it like that. And then we have also, with this length here is broken up this way. This length of 2 is actually 2 parts. As you know, this is the special right angle triangle we have here. And if this length is 3, right, 1, 2, 3, then this length is going to be 2 times the square root of 3, and this length here is the square root of 3. So we have, I was going to write that down here, the square root of 3. Then this little length here is 2 minus the square root of 3, which we can see is actually the slope of a 15-degree angled line. So that's an interesting little addition. And so we can see that that's the actual design of the 4. It's built around the fact that this circle contains the special right angle triangle, the geometry within its shape. Okay, so I'm just going to put the whiteboard behind to show you what that looks like. Okay, so there you go. That's why the numeral that represents the number 4 looks the way it does. The creators of the numeral wanted to point out, they wanted to use a special quality of geometry, the special right angle triangle. Here we have, the 30-degree line. For the 2, we had the 45-degree line. So we're going to keep working our way through different aspects of geometry, all those sort of foundational elements of geometry within these symbols. So that's the first 2. So now what I'm going to do is show you a larger version of this design here. We're going to go to, we're going to start to create the next rings in the series. We're going to look at a bigger pattern. We're just going to go over that, and then we're going to get into the 3, the 5, and just continue working our way through all of the numerals. All right, so this is that same pattern, and now we've included more rings. What I've done here is drawn, I guess that would be 21 more rings. So there's 25 rings in total. So the last ring on the outside edge here is the circle with the radius of the square root of 25. And we can see that it's landing on the 5 on the x-axis. So everything's lining up the way it should. But we're not going to be needing all of those rings. We're only going to be going up to the 11th ring because we're going to have 11 numerals in total, because again, we are in base 12. So now we're going to go and look at the 3rd ring in the series, and we're going to look at why the numeral that represents the number 3 has the specific shape that it does. So the 3rd circle in the series, the square root radius 3 circle, square root 3 radius circle, is different than the first 2 that we just looked at in that it doesn't have any specific lattice points that define its positioning on this pattern. The 2, obviously, we're just looking at that. It has those 4 lattice points, and then the 4th square root of 4 had those 4 lattice points. The 3 is kind of floating in between them, but it has been defined by this pattern. So the creators of these numerals always use the points that are existing already as the starting point for their numeral design. So what we're going to do is we're going to go to one of the points where these inner circles are crossing over each other as the starting point for this numeral, and then we're going to go to an actual lattice point that's quite close to it. So this is what I mean. We're gonna go. You can sort of see here. Here's the 3rd circle in the series. We're going to look at this point right here, one of the defining points that defines the actual position of the square root of 3, and we're going to start there. So now what I'm going to do is flip this board around, because for this numeral, we're going to be using the line that comes from the Dodecagon. So I'm hoping that you've already had a chance to look at my other video, my other submission in this contest, where I described to you the geometry of the dodecagon, where we had the lines that had the slope of going over 1 and up 0.7, because that's, again, a very foundational geometric element. It's new to us, but if you were already doing base 12, you'd be familiar with that. Obviously, they created 360 degrees using that dodecagon. It's very foundational in base 12 geometry. So now we're going to use that, the geometry of the dodecagon, to help come up with the design for the numeral that represents the number 3. So I'm going to flip this board around, because here I have that dodecagon, those lines on here. Again, it's the same. You can see the same circle pattern, but these lines here are not the 30, 45, and 60 degree lines. Well, that is the 45 degree line, but these two lines here are the lines from the dodecagon pattern. So they have the slope of going over 1 and up 0.7, or up 1 and over 0.7. So we're going to be looking at this line here, so you can see where that, because if you remember, you can see these lines are very close to the 60 degree line. So this point here is very close to the one we were just looking at that defines the square root of 3. So what I'm going to do is put my clear board behind, and we're going to start tracing out some of the lines again. Okay, so what I'm going to do actually is I'm going to write down the lattice points of these particular points, because they're kind of new. So you go up 1 and over 0.7, and then we're going to go up halfway. We're going to go 1, 2, 3, 4, 5, 6, and over 1, 2, 3.6. So the lattice points of this point right here, the coordinates are 7 plus 3.6, so that's 7, 8, 9, A 0.6. So the x-axis is A 0.6, and then the y-axis is 1.6, so the y-coordinate is 1.6. So those are the coordinates of this point here, and it's sitting on that dodecagon line. And now we're going to trace that line. We're going to go along here all the way up to this point here. So again, that's a point directly on that dodecagon line, and the coordinates of this point, the x is 1.9, and the y is 3. So there we have a 3 already, and now what we're going to do is draw a line across here, and we're going to go the length of 1, 2, 3, just to there. That's right. Is that right? Yep. Okay, so that's the length of 3. I'll put that 3 just like there. So the coordinates of this point here, the x coordinate is negative 1.3, and again the y coordinate is 3. So now what we're going to do is trace the outline of the circle. This with the radius of the square root of 3, we're just going to do it like this, going around, and we're going to stop here, basically where this would be where the that degree line is going through. So this circle here is exactly half of a circle. Okay, so I'm just going to leave it like that. So that's why the numeral that represents the number 3 looks the way that it does. And you can see that, again, there's lots of 3's in there. We have the length of 3 here. We have the length of 3 as the distance from the center to this line here. And we also have the decimal version. Here we have 1.3, and here the distance from the 2, this is 1.9. So again, there's a decimal, 0.3 from this line to the edge. So we have the decimal version of 3, the length of 3, the height of 3 from the center. We have the circle with the radius of the square root of 3 as part of the pattern. There's a lot of 3 incorporated within the symbol that represents the number 3. So I'll put my whiteboard behind just so you can see that more clearly. Okay, so there you go. So now we've done the 2, the 3, and the 4. Now we're going to go to the 5th circle in the series, and we're going to look at why the numeral that represents the number 5 has the distinctive shape that it does. Okay, so now we're back to this version of the pattern with this circle pattern in the center, and we're going to go to the 5th circle in the series, and we're going to look again at the lattice points that define its position on the grid. So we go 1, 2, 3, 4, 5, and we see that this particular circle has 8 points where it's sort of touching down on the coordinate plane beneath. So I'm just marking those points out right now. There they are. Those are the defining points for, or defining lattice points for this pattern. So the first thing that I'm going to do is trace out that pattern, or trace out part of the circle. We're going to start here, and I'm just going to go along, going through these lattice points here. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, just like that. And now what I'm going to do is also from this lattice point, again, we're working off of lattice points. I'm going to go up, draw a line straight up, the length of 2, and then I'm going to go along here, the length of 3, ending at that lattice point right there. So I'm just going to draw, or say that's 3, and that's 2. So of course 3 plus 2 is 5. So again, we have the value of 5 incorporated in the symbol that represents the number 5. So we have the length of 2 and 3. We also here, between these two lattice points is the length of 4. 2, 3, 4, and 5. And what's interesting is you could also kind of connect these dots here through the center to there, to this, you know, the points basically from one end of the numeral to the other. And we have a line that is basically being defined in units of square root of 5. So similar to how the 2 incorporated the line with, you know, the line that was broken up in units of square root of 2. Here we have a line, it's implied, that can be broken up into units of square root of 5. Okay, so I'm just going to leave it like that for this one. I'm going to put the board behind so you can see what that looks like. That's the numeral that represents the number 5. And so now we're going to go to the next circle in the series, the circle with the radius of the square root of 6. And we're going to see why that particular numeral has the shape that it does. All right, so we're going to stay on this side of the cardboard sheet. We're going to stay with this pattern, and we're going to go to the 6th circle in the series. And so the first thing that we want to do is use this pattern to generate the point that we would use, or the points to actually, you know, find the positioning of the square root of 6 radius circle, because again, it's like the 3, there are no specific lattice points that define its position on this diagram. So what we would do is we're going to use this pattern already. With the square root of 4 circle comes down and it intersects here. This is the same point that we were using for the 4. And we have this point here, which is, you know, the distance square root of 3. And I guess we could look at this point also. If we connect those points like that, we could get a line going up like that. And if we do the same thing over here using, let's say, these 3 points here, we could draw a line connecting those 3 points, and those 2 lines up and down, that's a square root of 3, square root of 3. Basically, it's sort of a version of the Pythagorean theorem where we find this point here, and that's going to be the square root of 6. So this point here, so again, what we're going to do, there's no actual lattice point there. We're going to go to a point just outside of that circle, and that point there has the coordinates of 1.9 and 1.9. So it's the x is minus 1.9 and the y is simply 1.9. And so that's the point that we're going to use to work off of for the line of the numeral that represents the number 6. And as we know, that symbol also has a complete circle as part of its design. So I'm just going to draw that in right now. So 1, 2, 3, 4, 5, 6. I'm just going to trace that complete circle. Okay, so again, we're going to be starting at that point. And now what I'm going to do is draw a line at a 45-degree angle going up in that direction. So I'm just going to mark off those points now first. Okay, I'm still on the screen, that's great. Now what I'm going to do is connect all of those dots. Okay, and that is the symbol that represents the number 6. So why does it look like that? Well, first of all, let's look at this the coordinates of this point here. The x is 2.6. So 2.6. So again, we have the decimal version of 6 right there. And then the distance going up the y coordinate is 1, 2, 3, 4, 5, 6 also. So 2.6 and 6 are the coordinates of that point. And now what's also interesting about that line is that as it goes up through all of these squares, it is landing, because of where it started, it's landing exactly in between each of these sections of 1. So in base 12, remember we're in base 12, half of 1 is 0.6. So again, we have the decimal version sort of encoded in that 45-degree line that's intersecting all of these, these ones exactly halfway. So that's why we have that line there. So we've got the height of 6 here. We have 2.6, and this is the point that we start. So again, that point is just outside of the square root of 6 radius circle. Now what I want to do is we're going to figure out the length of that line and see how close is that length of that line to the length of 6. So we can see that it's going to be in units of square root of 2. So it's not going to be exactly 6, but how close is it? So we can figure that out by creating a right angle triangle. We just kind of go along here, do something like that. Come down here, something like this. So the length of these two sides is 4.3. So 4.3 and 4.3. So I'm just going to pause the video. I haven't memorized all this math, and then I'm going to do that and then come back to you right away. Okay, I'm back. So 4.3 squared is 16.09. So doing the Pythagorean theorem, a squared plus b squared equals c squared. 16.09 plus 16.09 equals 30.16. So this length here is the square root of 30.16. So 6 squared, if this line was exactly 6 squared would be 30, so it would be the square root of 30. So it's a little bit longer than 6, but how much longer is it? Well, I just did a little bit of calculations to figure out what number multiplied by itself equals 30.16. And down here I found out that 6.016, that number squared, equals 30.16023. Okay, so that's 6.016. So from here, 1, 2, 3, 4, 5, 6, and then 0.01. That means it's inside that first little square. It's not that first square, but if you divide that little square up into 12ths, it's inside the first square in that section. That's how much longer that line is. So it's a very small, tiny amount longer than the actual length of 6. I find it very surprising that they were able to take the circle with the radius of the square root of 6 and just draw that one line. By choosing that point and drawing one line, they were able to get this, 2.6 and all those decimal versions, have the 6, and then also have so much 6 again in this particular numeral. Okay, so that's why the numeral for the number 6 looks the way that it does. Now we're going to go to the next circle in the series. We're going to find out why the numeral 7 looks the way that it does. Okay, so now for the numeral that represents the number 7, we're going to go to the 7th circle in the series. We're going to find its position again by working off of this original pattern, because again the circle with the square root 7 radius circle doesn't have any lattice points that define its position. So what we're going to do is similar to what we did for the number 6, but on this side we're going to start by drawing a line up here parallel with the square root of 3. So we use these points here. Here's the square root of 3 where it's intersecting here. We can go off those lines and go straight up to where that line intersects this where the y is 2. So that's the length of 2 squared is 4. So we have square root of 4 plus the square root of 3. We create a triangle there, and we're landing on the point is the square root of 7. And then what they did is they went to a point again just outside of that point. So we're going to go to a point that has the coordinates where the for x it's 1.9, and then the y is 2. Okay, so that's the point that we're going to start with, just outside of where these lines land. And what I'm going to do now again is flip the board around, because again, similar to the 3, they decided to use the line with the slope of over 1 and up 0.7. So it makes sense that they would choose that line to be part of the design for the numeral that represents the number 7. Okay, so we'll flip the board around so that we can use the lines that are already existing here as part of our diagram. So again, we'll line that up like so. So again, here we are, 1, 2, 3, 4, 5, 6, 7. Again, we've got those points. I'm just going to erase these lines here so that we're working with a clear board. And now what I'm going to do is count along this line here. We're going to basically draw a line to the corresponding spot on the other side here where that circle is again crossing. We're going to draw a line that is basically there. So the coordinates for this point is minus 1.9, negative 1.9, and then also 2 for the y. Did some good brackets. So the length of that line is 3.6. Okay, so now what we're going to do is we're going to draw a line going down that way with the slope of the Dodecagon line, which is down 1 over 0.7, down 1 over 0.7. So what I'm going to do is just slide this over so I can trace this line here, which has that exact same slope. And so what I'm going to do, the length of that line, well, it's going to go like this. It's going to go 1, 2, 3, 4, 5, 6, 7. Just like that, and you can still see it there. Yes, okay, great. So I'm going to slide it back to where it's supposed to be, like that. And we can see that now we have the length or the height of 7. This symbol has the complete height of 7 from the top to the bottom. Now I'm going to show you something that's really interesting. I'm just going to grab my compass. All right, got my compass. So what I'm going to do, I've set it up now. I'm going to put my compass point on this point here. I'm going to set my compass to the length of 3.6 so that it lands at this point here. Now watch this. As I go down, we can see that the compass, it's landing on this point right here. So I'm going to make a point right there. So that point, we have the length of 3.6 and 3.6. So that's 3.5 and 3.5. So 3.5 plus 3.5 is 7. So another way that the length of 7 is incorporated within this symbol. So then what they did in order to demarcate that point is they drew a line right here. So this is the origin of why you see some number or numeral 7s have that line across. That is actually the original design. And what I'm going to do is make a point right here and right here. I'm going to draw a line between those 2 points. And you can see these points are defined by where the Dodecagon line is going down on either side. Again, this line has the same slope of down 1 and over 0.7, and or down, 1 and over 0.7. So this line here is the length of 2 times 0.7. So now again we have the decimal value incorporated, not only in this line here, but also in the slope of the line, similar to how the 6 have the decimal version of 6 incorporated within its line. So that's why the numeral 7 looks the way that it does. And I'm just going to say obvious, well, maybe not obviously, but this is an angled line, so it's not 100% exactly the length of 3.6. It's really close. I'm going to leave that though for you if you want to figure that out. A lot of these symbols that I'm showing you, there are other kind of even deeper geometrical qualities about the number and the numeral that you can explore later at your own. I'm just going over the basics. There's so much information in all of these numerals. It's really quite amazing. But that gives you the basics, why the numeral 7 looks the way that it does. Okay, so there you go. Again, the height, 3.6 plus 3.6. Those are the coordinate points there. Goes down to here, and 0.7 and 0.7. Okay, that's why the numeral 7 looks the way that it does. Now we're going to go to the next symbol in the series, the numeral that represents the number 8. Okay, the numeral that represents the number 8, we're going to go to the 8th circle in the series, and this circle you can define by lattice points. So here it is, it's basically 2 root 2, or 1, 2, 3, 4, 5, 6, 7, 8. So the 8 is defined by 4 lattice points. There's one there, there's one there, 1, 2, there's the one there, and finally one here. So now we're going to draw a symbol that is touching down on those 4 lattice points, and we know what the 8 looks like. So what I'm going to do now is basically draw 2 circles. Okay, so we're just going to put the compass there. I'm going to draw 1 circle up here, and I'm going to draw 1 circle down there. Okay, not great circles, but that's okay, so you get the idea. And if you look at the height of this symbol, starting from the top, going down, 1, 2, 3, 4, 5, 6, 7, 8. So again, the value of the number is encoded within the symbol, and we have the symbol that represents the number 8. Okay, pretty straightforward. I was experimenting with other versions of that, but I always came back to this as the final one because really it's so simple, seems quite elegant, and it's interesting. Basically, those are 2 symbols with 2 circles with the diameter of 4, and so obviously 4 plus 4 is 8. It's interesting to note that the numeral for the 4 had no circles in it, no curves. A lot of the numerals do, and this symbol has no straight lines, which again a lot of the numerals do. So it's kind of interesting, all lines, no circles, all circles, no lines, kind of the back and forth, the 4 and the 8. Anyway, that's why the numeral 8 looks the way it does. I'm just going to leave it like that, and we're going to go to the next circle in the next symbol in the series. We're going to look at why the numeral that represents the number 9 has the distinctive shape that it does. All right, so the numeral that represents the number 9. So for this one, I've had to turn the board upside down in order that we can accommodate the long line that is part of the 9. So the first thing I'm going to do again is mark off the 4 lattice points that define the circle with the radius of the square root of 9, which is basically 3. So we're going to start here and just go over 1, 2, 3, and 1, 2, 3, and 1, 2, 3, and 1, 2, 3. I've got that mark there already, and I think you can see it. So I'm going to trace out that circle. We already know what the 9 looks like. It's got a complete circle as part of its design. And then again, coming off one of the lattice points, we're going to come and draw a line off of this lattice point here. We're just going to go straight down the length of 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And I think you can see that there. That was my test to make sure that this all fit in, but it does. You can see that it all fits in the screen. So that's why the numeral for the 9 looks the way that it does. We've got the length of 3 in there as the radius of the circle. We've got the length of 6 for the diameter. We've got the length of 9, and then we have the length of 10, basically in base 12, 9, AB 10. So the 9, you know, it's a very simple, in a sense, elegant shape in that it's very, you know, one circle and one straight line. The 9 there's a sense of completeness to me. It's, you know, the fact that it's the square root of 3, it's very balanced. You can get kind of philosophical about it, but basically that's what I believe is the correct version for why it looks like that. That's why the numeral 9 looks the way that it does. At one point I was considering perhaps this line was just the length of 6 and the whole symbol was the 9, but I think this is the right one. That length is the complete length. Those are the correct proportions. That's, again, you know, just as an aside, all of this is just me kind of toying around with how the geometry works, how it lines up. That's why the numeral 9 looks the way that it does according to my theory. Now what we're going to do is go into the next 2 symbols that are the ones that are really base 12 symbols. So the next one is called dec. It looks something, you can draw this here, like an X, but it's an X with one side having these little marks sticking out, little like a little hockey stick type of mark going out either side. Where I learned about this symbol even existing was on a Numberphile video, so a shout out to Numberphile. They did a little video on base 12 and they introduced this symbol, and then the next one after that is called L. It's called, you know, dec and L, and basically, you know, they were just drawn out by hand similar to how I'm doing them now, and from that shape I was able to play around with them and the geometry and the idea that there's, you know, hidden math in there. Now these 2 symbols, it starts to get a little more intense in terms of the design, how they chose to fit it in. But you're going to see, again, we're going to go to the 10th circle in this series, circle with the radius, we would say the square root of 10, square root of dec, and we're going to see why they chose to create this symbol to represent that number. Okay, so for this particular symbol, we've gone to the other side of the board again because they decided to use one of the Dodecagon lines for this particular line. So I've already drawn this symbol out and written some of the coordinate points because it's a little bit more complex than the others. Actually, what I want to do, this particular circle does have lattice points that define its position in the pattern. It has 8 lattice points, but they didn't use any of those lattice points for this particular symbol. So I just thought what I might do is actually just trace that circle so you can see what it looks like, its position and relationship. So here it is, you know, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or dec. So it goes around like this. Okay, something like that. So this symbol is just sitting on the inside of that circle. So what they did was they chose, I'll start with this line here, the Dodecagon line. They are following that line up, and again, you remember the slope of that line is up 1 over 0.7, up 1 over 0.7, then they went up half, so up 0.6, and then over half of 0.7, which is 0.36. For this point right here, that's where we're starting. So 1 plus 1 plus a half is 2.5. So I think you can see what's happening here. We've got a height of 2.5 and then a sort of depth of 2.5. Basically, the distance from this point here and that point there is 5. 2.5 plus 2.5 is 5. And then 5 plus 5 is dec, or 10. So from that point, then we go over in a straight line the length of 0.5. So the coordinates of this particular point is, again, the y is 2.6 and the x is minus 1.6. That's 0.7 plus 0.7 is 1.2, and then plus 3.5 is 0.56. So negative 1.56. Then we add 5 to that, or subtract 5, however you want to do it. But you get the x of this point here, the x coordinate is negative 1.86, and again the y is 2.6. Here it's the same, but negative 1.86 and minus 2.6. And then of course it's all the same down here. So again, 0.5, and then this length also 0.5, 0.5, 0.5 is dec, or 10. So they've incorporated the decimal value, and they've touched down just on the inside of the circle positioning. So this line is coming straight, but this line here is not the dodecagon line. It's a little bit off, and we're just drawing a straight line from this point here up to that point there, or here also. So this is 1.86 is the x coordinate, and then 2.6 for the y. So that's what that looks like. I'm going to put the whiteboard behind so you can see that. Okay. So that's what that looks like, but now we're going to go a little bit deeper into this symbol, because there's more here than just the fact that they've incorporated the value of the number that they're representing and the decimal value. What we're going to do now is look at the triangle that's formed by connecting this point here over to this point here, and then up to this point there. So we just figured out that the length of this side here is 5. Whoops, so 5. So I was going to put a 5 there. And then I'm going to kind of point out that 5 squared, again, duodecimal, is 21. Okay, so we're going to use, well, let's figure out what the length of this side down here is. We got negative 1.86 and positive 1.86. So I just got to get my piece of paper from the floor here. Okay, got it. So 2, I think you can see that, yep. 2 times 1.86 equals 3.9. So I'm just going to write that here, 3.9. So that's the length of this side here. So 3.9 squared equals 12.009. Okay, so far so good. So now what we're going to do is find out the length of this side. So we're going to add, I'll do that up here, 21 plus 12.09, we get 33.09. I guess I could have done that over here. So the length of this side, a squared plus b squared equals c squared. This side equals the square root of 33.09. So what's interesting about what's happening here, 5 is, what was it again? 4 times 1.3 equals 5. 0.3, 0.6, 0.9, AB 10, so 1, 2, 3, 4, 5. And then 3, really small here, 3 times 1.3 equals 3.9. So if now we're going in units of 1.3. So we have 3 times 1.3, 4 times 1.3, 5 times 1.3 is 6.3, right? 6.3. And 6.3 squared equals 33.09. So what that means is that the proportions of this triangle, it's a 3, 4, 5 triangle. So they also incorporated a 3, 4, 5 triangle in the designs of this symbol for dec. So part of me thinks there must be some connection perhaps between the 3, 4, 5 triangle and the dodecagon. So that is something that I haven't quite figured out yet. I don't know if that's right or not, but that's just intuitive because they're combined here. Might not be, but maybe it's something to look deeper in. That's a fairly recent discovery of mine, this 3, 4, 5 triangle hidden in there. But that's some more geometric information that's incorporated within the symbol for dec, which is the 10th circle in the series. Okay, so now we're going to go to the last circle in the series. This is going to be the square root of L, or 11, radius circle. So we're going to go to the 11th ring on the pattern and see why that numeral has the particular shape that it does. Okay, so for this numeral, the numeral called L, we're going to start here actually, because for this particular circle, just like the 3 and the 6 and the 7, it doesn't have any particular lattice points that define its position within the pattern. So we're going to have to work again off of this initial diagram to create a point that we can use to draw the circle. So what we're going to do, I've decided to use this big version because it's a little bit more complex. This is actually probably the most complex symbol of them all, so I'm just going to go slow through the geometry. It's simple, but there's a lot of steps. So the first thing that we're going to do is just mark off these 4 points here. So these are the points on the circle with the radius of 1, and they are on the 30-degree angle, in all directions. So what I'm going to do now is draw a line just connecting those points across like this, all the way out to the square root of 3 radius circle where that crosses there, and mark that point there, and do the same thing on the bottom, going across like that to this point. It's actually down here like that, something like that. Okay, so the dimensions, let's just use this as an example of this triangle right here. That's a 30-degree triangle. Just to go over that quickly, again, the dimensions are 1 and 2 and the square root of 3, 2 also being the square root of 4. You can see that okay, yep. So this, if this length is 1, then this is going to be 0.6. So this length here is 0.6. So what we want to do now is figure out what the length of this is here. If we connect these two lines like that, what's the length of this bottom line? We have this distance here of 0.6, and the hypotenuse of that triangle is the square root of 3. So I'm just going to draw that out here, and I will put the whiteboard behind it at the end so you can see it. So we have a triangle with the dimensions of 0.6 and the square root of 3. So we can use the, sorry, that's not the square root of 3. This one is the square root of 3. There. So we can use the Pythagorean theorem to figure this out. We're going to be doing c squared minus a squared equals b squared. So c squared, the square root of 3 squared, is going to be 3. And we're going to subtract this side here. So, b squared, 0.6 squared equals 0.3. Again, duodecimal, or base 12 math, 6 times 6 is 30. So 0.6 squared is 0.3. So 3 minus 0.3 equals 2.9. So this side here is the square root of 2.9. So this side here is the length of 2.9, or the square root of 2.9. Okay, I think that's all pretty clear so far. So we got a line going out here, the length of 2.9, and we have a line going up here, heading up, and position on the, well, at a right angle like that. So now what I'm going to do, that's just to sort of get that, all the positioning. Now I'm going to switch to the board, a little more condensed version of this diagram, and we'll see what we can do about finding the exact position of the circle with the radius of the square root of 11. Okay, so here we have the same diagram and the same lines. I haven't got any numbers in there, but you can see this line going up, and here we have this, we can see it's intersecting the 30-degree line. So now we have a right angle, special right triangle like that, with the dimensions of 1, 2, and the square root of 3, just, so on its side, right here. Of course, this is here's our middle line, like that, and we just I'll draw it. Well, here it is basically, and then this goes like that. So this length here is the square root of 2.9, and so what we want to do is figure out what this length is. So if this length, now basically to multiply all these sides by the square root of 2.9. So to find out what this length here, so square root of 3 multiplied by the square root of 2.9 equals square root of 8.3. You can test that if you get out your base 12 calculator. So now what we want to do is figure out what this length is. So again, a squared plus b squared equals c squared. So basically these are both square roots. So if we square a square root, we're just going to be doing 2.9 plus 8.3. So 9, a, b, 10, carry the 1, 8, 9, 10, 11, or 8, 9, dec L. So there's our L. So this side here is the square root of L, or B. I may be interchanging back and forth. I'm used to calling them A and B, but basically dec and L, trying to stay consistent. So now we have a point up here. If we didn't already have that circle, we would be able to draw our line up where it basically intersects with the 30-degree line, which was originated from this pattern. So now we've created a point here that is the point that defines the square root of L radius circle. And of course we could do the same thing down here, also like that. We've got this line already going out, and this line intersects, and we know it's going to intersect on the point of the square root of L also. So what I'm going to do now is draw the circle in with red, just so we can keep track of it. Okay, and by doing that, of course, we already have our X and Y axis taken care of. So we can see now we've created a point over here where we're also going to be using, we've got 3 points, and all of these points, again, are equidistant from each other. And that's what we want to do. We want to create a shape that's basically gives us, we got a point here, a point there, and a point there. That's basically what we're working with. We got a point here, here, and here. We've created something of a giant equilateral triangle. So I can draw that in as well. I'm just going to draw with my hand something like that and like that. So there's some sort of the bones or the points that we're going to work with. So now what we want to do is figure out where, it looks like we have to draw 2 circles now. And the question is, where is the center of that circle and what is the radius of that circle? So I'm just going to clean this board up a little bit so that we can see more clearly what we're working in, and then we're going to see if we can figure out where those points should be. Okay, actually I wanted to go back to this for a second because I just noticed something as I was playing around. I had to readjust my board for the next part, and I just did the math on this side. One of the sides, are basically they're all the same length, of the equilateral triangle. Again, this length here from the sort of center, or half of the length, is the square root of 8.3. So the total side of that triangle is going to be 2 times the square root of 8.3. So to figure that out, we square 2, turn into the square root of 4, times the square root of 8.3 equals the square root of 29. So it's kind of interesting that this length is the square root of 29. This little length in here is the square root of 2.9. There's an interesting correlation there, or maybe there isn't, it could just be a coincidence, but in base 10, this would be 2.75, and this would be the square root of 33. So I just find it interesting, every now and again this happens where there's numbers that are lining up in base 12, where in base 10, you don't really see any correlation. So I don't really know what the correlation is between those 2 numbers at this point. Again, the geometry of these numerals just keeps popping up with new information, and it's taken me a long time to get to this point. There's probably more stuff in here, but we haven't even finished yet. So I just wanted to show you that. And so here's my y coordinate. So what I'm going to do now, the point that we're going to make, the point that's going to be the center of the circle that we're drawing is this one here. It's on the 90, 100, 120 in base 10 degree angle. This, the 30 degrees off of this 90 degrees. Sometimes it's a little difficult keeping all the base 10, base 12 in my head. But we're on this line right here, that degree line, and the y is going to be at 2.5. So 1, 2.5, and then we're going to draw a circle with the radius of 3.1. So 3.1 plus 2.5 is going to be 5.6. So that's going to be 5.6 from the center up. And then we're going to draw another circle like that down here. And so 5.6 plus 5.6 is going to equal L, or 11. So we're going to have a symbol with that whole entire height. And actually I can probably draw that for you right now and just show you what that looks like. And then I'll clean up the inside to carry on with the geometry. Okay, I'm going to rub this out now. All right, so this is why the numeral that represents L looks the way that it does. We're going to connect these 3 points here. So here's that point right there. Put the compass here. So I've already set the compass for 3.1. It's going to go up like that, and around and down like that. And then I'm going to do the same thing down here. Here is that point there, I believe. 1, 2, 3, 4, 5 right there. Put the compass here. Wait, that's not the right. No, sorry, it's over here. That point there. Okay, so go like that, and like that. Go down. Just get over that lump there. Like that. Okay, I'm a little bit off, but basically that's, of course they're the same. That's why the numeral that represents L looks the way that it does. So now what we're going to do is just look at some of the geometry of this 3.1, where it's landing, what that triangle is, and all that. So I'm going to clean this up a little bit, and then we're going to go a little bit deeper into the geometry behind this symbol. All right, so I've written some more information on the board here. I'm just going to go over it all and explain what it is you're looking at. And then I'll put the whiteboard behind at the end so you can see it clearly. So we've drawn this circle with the radius of 3.1. So here's r equals 3.1. So when we square that, 3.1 squared is 9.61. So the length of that line is also the square root of 9.61. And so here, this height here, that was our y, which is 2.5. So 2.5 squared is 5.A1. So the length of this line here is the square root of 5.A1. So a squared plus b squared, c squared. This is our c squared. So c squared, 9.61 minus our b squared, 5.A1, equals b squared, 3.8. So this length here, from this point here to that point there, is the square root of 3.8. So if you were to plug into your calculator 1 point b and square that, you would get 3.81. So this length here is the, again, square root of 3.8, which is very, very close to 1 point b. So there we get our decimal point. And again, I'm going to be alternating between point b and L. It's the same. I think I mentioned this already, that just used to saying b, but b and L are the same numeral. So that's this triangle here, 1 point b. So that we also have this triangle here, which is another special right angle triangle with a 30-degree angle. So we know that those proportions are 1, 2, and the square root of 3. So this side is the length of 5.A1. So what number multiplied by the square root of 3 is going to equal 5.81. So we're going to divide that side by the square root of 3. So the square root of 5.81 divided by the square root of 3 equals the square root of 1.b44. So then again, another 1.b is showing up here. So that becomes this length here. That's 1. So this is the square root of 1.b44. Now again, if we were to plug into our calculator 1.49 and square that, we would get 1.b469. So 1.49 is very close to the square root of 1.b44. So that's the length of this line here, this section of line. So if we add these two together, this 1.49 and 1.49, we get 3.39, and that's the beginning of the irrational number that is the square root of L, which is again the total length of this line to that point there. Okay, so our x coordinate is going to be negative, well, basically negative square root, or negative 1.49 or 1.b44. I think that's the right way that you write it. Okay, basically I'm just going to leave it at that, I think. You can see, again, we've got a whole lot of like decimal versions of the number that we're working with. We've got the height of the number that we're working with. A lot of geometric information in there. We've got an equilateral triangle. A lot of geometric stuff going on. Whoops. Okay. Okay, so that's what that looks like there. I think I'm just going to leave it at that. I have to admit I'm feeling a little bit rushed because I'm trying to get this finished and then processed and into the contest. So I realized I think I haven't done the 1 yet. I started with the 2. I've gone all the way to the L. So that's what that looks like. I'm going to clean off the board. I'm going to go back to that original big diagram at the beginning and show you what I think is the original version of the numeral that represents the number 1. And then we'll wrap this up and I'll hopefully be able to get it in for this contest. Okay. All right, so the numeral that represents the number 1. So again, we're going to be working off of the very first circle in the series. That's this one here. We're going to go to one of the lattice points that defines the position of the circle. I'm going to go to this one right here. I'm just going to draw a straight line going from that point there to that point there. This basically is on the square root of 2 circles. So we have a line that is the length of 1, again, keeping this whole thing going. And so what I'm going to do now is just trace the edge of that circle. I'm going to go to this point right there. Okay, so that, I believe, is what is the original version of the numeral that represents the number 1. So that's where the curve comes from that you see in so many numerals that represent the number 1. There's that curve up there. So a lot of ones, maybe they look like that. They got something like this going on, or they're just like that. Basically, people all over the world draw their ones differently. Some people just do a straight line, and then there's a lot of variety as to how much of a curve is in that first little swoop. But again, I think this is the original version right there. And what's really interesting about this pattern or that particular angle, well, for one, there's the fact that it is a 30-degree angle. If I swing this over and go put it there, you can see that point is also the same as the 30-degree angle that's going on like that. And you can draw this line over like that or something. So it contains that sort of geometric information. And it's also interesting as you slide it going that way. Here, the gap between basically the curve and the circle, that distance here is, remember, we're in base 12. So that distance, if we were to count that, here we go, 1. See how we got all these points here where the circles are intersecting each other. You go all the way around, there, am I on the right circle still? Yeah, there. So here we are, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, 10. So this sort of empty space in there is 0.1 of the circle. So it's kind of the decimal value of 0.1 kind of contained in there. There's the 30-degree angle in the relationship to these 2 points. Both of these points here are the distance of 1 from this point here. That's the length of 1, and that's the distance of 1. And this section of, well, you know what? I'm just going to leave it there. That's why I believe the numeral that represents the number 1 looks the way that it does. Actually, I'm going to go to my other drawing of this to show you what I'm talking about in terms of sliding that symbol over on this pattern. Okay, so here we are again, the smaller version, that straight line with the length of 1, the curve there, and we've got this point is being defined by this symbol. So when I slide, you know, here we are on the 1 and then the square root of 2 line. So we go over like that. We see this point lines up again, but now it's on the square root of 3, and then this is the square root of 5. So the gap between them is 2 units of, basically these circles, each of these rings has the area of 1 pi. If you use the formula for calculating the area of a circle, pi r squared. So here our r is always the square root of 2, 3, 4. So, you know, the first circle has the area of pi. The second circle, the total area inside it is 2 pi, so 2 minus 1 is 1. So that's, you know, 1, so here you have 3 minus 2 is 1. Again, so each of these rings has the area of 1 pi. So in this first space here, we're sort of delineating an area that has the area of 1 pi. And over here, we have an area that has delineating, so the rings of 2 pi. When we go over here, now there's 3 rings in between. This circle, this is the point on the, see, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then A. And then as you continue on, here is the point 1, 2, there's 4. And of course out here we've got 1, 2, 3, 5, and so on. So I thought that was kind of interesting. Another, you know, a little bit of geometric information encoded within that symbol. I think, again, that this is the original version of the numeral that represents the number 1. Okay, so that is it. That's for my presentation. I hope you've enjoyed it. I do have a YouTube channel called Duodecimal Division. I have produced a series of videos, this exact same information, called Secrets of the Numerals, where I go into them a little bit more depth, but really that's it there. There are a few other patterns within the patterns. The amount of circle here, see how this one here, you have one, you know what, I'll leave something for your imagination to discover on your own, and there may be more hidden information in these numerals than what I've gone over here. It's something to explore. It almost feels like a course in base 12 mathematics. You can see how on some of the numerals it's very important to approach them from a base 12 perspective, especially the last two. Those symbols are representing 2 extra numerals. The 6, the 3, the 7, we're using the Dodecagon, which is a base 12 shape now, we've discovered it. And the 6 has that, you know, that slant, the 45-degree line that's going through all of those ones at, you know, 0.6. So I find this whole thing very fascinating. So I hope you enjoyed that. Thanks for watching. And yeah, that's it.